Hey class, this is 16.3, 16.4. So we're going to start off with 16.3 with auto-ionization of water. As we've seen, water is amphoteric. That means water can go either way. It can be an acid or a base. In a pure water, a few molecules act as bases and few act as acids. In other words, water doesn't split up very well. As a matter of fact, it does so, but it does with very little concentration. You'll see what I mean in a minute. So this is the auto-ionization of water, which means that water will just break apart to a very small degree into H3O pluses and OH minuses. So if we take a look at the actual amounts that water will break up when it's pure and under specific situations or conditions, this equilibrium here has obviously a Kc. We actually refer to it as Kw for the equilibrium constant of water, for the auto-ionization of water. This number that we have is 1.0 times 10 to the negative 14th. This is a very, very small amount of breaking up, which means that most water is just water and not ions. Let's move on. Oh, that's it. Hang on a second here. There's not much more we can talk about. That means that this amount here is times 10 to the negative 14th. That means that if each one of these is x, that means x squared equals 1.0 times 10 to the negative 14th, which means if I take the square root of both of these here, what I end up with is each one times 10 to the negative 7th. That's both hydronium ion and OH, hydroxide ion, 1 times 10 to the negative 7th. That ends up being important later on, which is why we're going to talk about pH next. There we go. So what is pH? pH is the power of the hydrogen ion or the hydronium ion concentration. So to find pH, we need the negative log, and you can do that on the calculator, of the concentration of H3O plus. That's all it is, but this is probably one of three most important equations in this chapter. And this might be the first one. So very important. Please get pH equals negative log. We're going to do that pretty often, so you'll start to pick it up and be able to do it no problem. So here's where we talk about with pure water. Here I have my hydronium ion and I have my hydroxide. You know that just so that we're clear on this, in case you didn't pick this up because I didn't mention it before, but if this is our equilibrium, then of course all we would see in the K expression then, because these are both pure liquids, all we would see then is this. So it's not like we're leaving anything out that should be there. This is pure liquid, so it doesn't show up in the K value. That's why it just, you keep seeing the same two concentrations over and over again. So this says, because in pure water, these two are equal to each other in pure water, that means that we take to the 1/2 of that equals, that's what I was talking about before on the other slide. So let's keep going. So for pure water, pH of pure water then equals 7, the negative log of 1 times 10 to the negative 7th. This is where our pH scale comes from. So an acid has a higher H3O plus than pure water, so its pH is less than 7. This is why acids tend to be very, very strong. Acids are down in the 0 range, or even negative, slightly negative numbers for pH, and neutral would be 7, and then bases are higher than that. So a base has a lower H3O positive hydronium ion than pure water, so its pH is greater than 7. because remember we're talking about mostly this part here. So you can take a look at this. The pH of acids means that this value for a base is much less, which means that we have a value that's much less than 7. Neutral is when they're both the same, and basic is when this one is much less than this one, and our pH is then higher than 7. Okay, just take some getting used to. Take a look at some pH values for some basic things like black coffee or bananas. So I just ate a banana. Take a look at milk. Notice that these are all like pH of less than 7, which means they all tend to be a little bit acidic. Here's our citric acid, here's our carbonic acid, here's formic acid. And there is some hydrochloric acid in there, I believe. But then take a look at those things that are considered bases. Household bleach, obviously, is a big one. That comes up very basic. And ammonia, okay, dissolved in water. Borax, baking soda, eggs, those are all in the basic. Even human blood and tears is more on the basic side, if just a little bit. Moving on, the other P scales. Well, if you can do that for pH, if you can get pH equals the negative log of the hydronium ion, then of course you could do a POH. That measures the negative log of the hydroxide ion. Now here's the cool part about that. So pKw equals the negative log of Kw. So here's what you can do with this. This is nice. We know that this and these two equal this and gives us that. Negative log plus negative log is 14. The negative log of the Kw is 14. So pH, here's what this means. pH plus POH equals 14. So if we have a pH of 2.3, we can always find the POH by taking 14 minus the pH value, which would be 11, what did I put there? 0.70 for my POH. So just a simple subtraction problem. 14 minus the pH gives you the POH. That's an easy way. So this is another very good equation to know and to write down. So this is talking about how we measure pH. Many times we use a pH meter if we have to know the exact measurement for the pH, not exact, but very good, like accuracy. If we just need to know if something is more acid than it is base, then we can use litmus paper. We can use other indicators that you see here. Some of these are not very. Phenolphthalein is probably the most common one. Even if you've never heard that before, phenolphthalein, when you do chemistry labs, if you do chemistry labs in college, you will see that all the time. The rest of these are for very specific situations. So you may use thymol blue. I've used that before. I've never used methyl violet. Bromothymol blue is another one that ends up being a little bit more common, but not by much. The rest of these, like, I'm not even sure what they actually are. Maybe biology uses them for specific reasons. Honestly, I'm not sure. And obviously we talked about the pH meter. Okay, that's where we're breaking strong acids.